A sodium atom walks into a bar. The bartender looks up and says, "Hey, we only serve cations in this bar." The sodium atom says, "Well, I am a cation." The bartender says, "Are you sure you're a cation?" To which the sodium atom replies, "Yes, I'm sure I'm a cation, but I'm getting a really racist vibe from this bar, so I'm going to go get my drink somewhere else." So, anyway, thermochemistry. Thought we'd talk a little bit today about thermochemical equations. To start with, exactly what a thermochemical equation is, because a lot of students get a little confused by that. But all a thermochemical equation is a chemical equation that includes its relative value of delta H, enthalpy change. So, for example, a lot of you guys and gals, don't want to be gender exclusive, a lot of you folks, there, that's better, use gas heating to heat your home. Natural gas is mainly methane, and the combustion of methane, which we talked about a little bit earlier in the course. And the way that reaction is written, it gives off about 800 kilojoules of heat, about 802. Right. So that's an example of an exothermic reaction. And the way we show that in our thermochemical equation is we put a little negative sign in front of the amount of heat being released. Again, the negative is just a relative value. It's just you're just showing that you got a net loss of heat during the process. Kind of like accountants. Well, same idea. But another example of a reaction that people will commonly use as an example are cold packs. Cold packs. Thank you. But most cold packs, the way they're designed is they're usually, like this one here, is basically a little pouch that's got another little pouch inside. And if you shake it, you'll notice some liquid sloshing around, and you might hear something rattling inside. Well, if you look closely on that package somewhere, the solid is ammonium nitrate, and the liquid is just water. So all you're doing when you pop that inner seal and mix those two together, probably shouldn't do that on video, you're just dissolving ammonium nitrate. No, I'm not going to redo it. Which, as an ionic compound, it dissolves by dissociation. So in order for this process to occur, ammonium nitrate has to absorb 28 kilojoules of heat. And again, the positive sign shows that it's an endothermic process, which means heat's being absorbed by the reaction. And you don't have to put the positive there, since you see a number without a sign, you assume it's positive, but a lot of people like throwing the positive just for emphasis. So that's it. Chemical, thermochemical, chemical, thermochemical. And that's really all there is to it. It's just a chemical equation with the delta H sign slapped to it. So it really is just one big chemical equation, which means a lot of the stuff we talked about, how chemical equations work and are read, still applies. So with our methane reaction, the way we read it is that we tend to look at things on the mole scale when we look at an equation, like the coefficients. 1 mole of methane is going to react with 2 moles of oxygen, and you're going to release 802 kilojoules of heat and all the other products. Now you'll notice I didn't include the negative sign when I said release 802 kilojoules of heat, because again, the negative is just some relative thing we use so you can see that it's releasing heat without having to put the word release or lost in the equation. Again, it's just a relative sign. So you wouldn't say releases negative heat. That's like saying you lose negative weight. I lost negative 300 pounds. That doesn't make sense. So don't be confused by that. With our ammonium nitrate, our cold pack equation, For every 1 mole of ammonium nitrate, you're absorbing 28 kilojoules of heat. But what if you don't have, going back to our first equation, a mole of methane? What if you have 3.5 moles of methane? Well, if we were converting 1 mole of one thing to a mole of another chemical, we would just look at the coefficients in our balanced equation. Like methane to oxygen, 1 to 2. It's the same idea here because, again, it's one big equation. So again, for every 1 mole of methane, you're losing 802 kilojoules of heat. So that should give you about 2,800 kilojoules. So really all we're doing here is just stoichiometry. So yes, that thing that never seems to go away. Although if you're following the traditional order of things in general chemistry, this is probably the last time you run into it, at least in lecture. It never goes away in lab. Not even in organic. Nope. Sorry. No, sorry, not sorry. I really hate that term. Sorry, not sorry. Okay, not sorry, sorry, not sorry. I don't know what the proper response to that is, but I'm old. Who knows? But anywho, let's say you have 100 grams of water that's produced from this reaction. How much heat are you going to get out of it? So again, it's a stoichiometry setup, just like any other stoichiometry setup you run into. Convert this much of this stuff to some other amount. Only this, unlike previous cases like gram to gram stoichiometry or gram to volume with molarity, we're using, this is a grams to heat. But again, same idea. First step of any stoichiometry problem is to take what's given and convert it to moles. So we can do grams to moles with molar mass. Now, just like we did in the other problem, we look at our balanced thermochemical equation. And for every 2 moles of water, we're going to release 802 kilojoules. So that's the unit we want. And that'll give us 20 to 30 kilojoules of heat. My notes are in the way. There we go. And again, this reason that's a 2, I actually put the arrow in. I didn't bother pointing it out. The reason it's 2 is because there's a 2 in the equation. So again, it's just the same mole to mole conversion, sort of, kind of, that we looked at or did before with previous types of stoichiometry. So for another example, let's go back and look at our ammonium nitrate reaction, or equation. It's not really a reaction, it's just dissolving. Although I guess some people would call it a decomposition reaction, maybe. I don't know. Either way, this thing that I showed you a few slides ago. All right. Let's say you're releasing 3,300 kilojoules of heat. How many grams of ammonium nitrate does that correspond to? So again, it's the same stoichiometry setup. Convert this much of this stuff to this much of this other stuff, giving this equation. Only now it's something to heat, or in this case, heat to something. And instead of a chemical equation, it's a thermochemical equation. So again, you start with the unit that you're given. In this case, it's kilojoules. So first step is take what's given, convert it to moles. So according to our balanced chemical equation, thermochemical equation, it's 1 mole of ammonium nitrate for every 28 kilojoules of heat. So now we're in moles of the thing we want. We need to convert it to grams, which again, that's molar mass. So ammonium nitrate's molar mass is a tad over 80 grams per mole, and that puts us into grams, which gives us 9,400 grams, or 9.4 kilograms. So again, thermochemical equations, they're just chemical equations. Just somebody put a delta H sign there because that's important for whatever thing you guys are currently talking about. And a lot of the stoichiometry that you're doing in this part of the course, it's the same stoichiometry you've done before. For the most part, it's set up the same way. Convert this much of this stuff to this much of that stuff. I've said that like 3 times, I think, so far in this video. I say it a lot more in class because you're just going to hammer that point home. And again, just the first step is to take what's given, convert to moles. which is what you did before. If you're given a mass, you can convert it to molar mass. If you're given the heat, then you just use the balanced chemical equation to convert the amount of heat that's given to the moles of whatever it is you're trying to convert to. So that'll be it for this time. Whatever time this is for you. For me, it's a week. Whatever. Bye. A sodium atom walks into a bar. The bartender looks up and says, "Hey, we only serve cations in this bar." Fuck. Do it again.